berhenti ke tu.
Just switch off one. You want two aircon or one? I think one. Okay, I think let's begin with our lectures today. Okay, this is what we have learned so far. Okay, for the past few weeks. Okay, from let's say week 1 to the last week. Okay. Alright, so we went through some of the very basic of the power electronics, right? And some review of what is the three-phase, okay? And some of the power diodes, transistors, synchro and cyclo converter, which to change the frequency. Alright, so today I'll be covering the converter technologies, okay? And followed by some of the so-called the propulsion oscillatories, right? That we will be covering today. So this will be the last two chapters, okay, for this semester. Alright, this will be topic 7. Okay, what is inverter? Okay, I think you have come across this in the previous topics, right? It's basically what we are trying to do here is to convert, alright, from AC, alright, to DC, alright, through the rectifier. Okay, you just remember the rectifier terms. You can convert AC to DC, and then back to the AC again, alright. But this stage, alright, we are trying to change the frequency. Okay, we are trying to change the frequency. So once we change the frequency, what we will get is a different speed, okay, that the motor will experience. Alright, this is what the whole process of the inversion is all about. Okay, so in the practice, alright, how we try to configure this type of system, alright, you will see that the inverter consists of basically two parts that I mentioned in the previous slides. Okay, the AC, okay, which is the power source, three-phase. So it will go through a diodes, alright. This bridge will help to rectify, okay, from a sine wave, the sine wave, to a wave form that is almost appear to be a constant DC line, okay. Alright, and this smoothing capacitor is to really make the whole DC line less humps, and it's more smooth, like really a straight line, okay, if the frequency increase. Okay, so this part will help to actually increase the frequency, alright, or reduce the frequency. Okay, so sometimes you know that from the inversion process, alright, you will find that is some of these the parameters that's given to you is in terms of the frequency range. Okay, so how much you can change. Alright, so you can see that as I just explained. Okay, so basically this diode will help to transform the negative half cycle to a positive half cycle. So you can see that don't really look like a DC yet. Okay, but if you use the capacitor, as you can see from here, so you only have a waveform that's mainly on top of it. Okay, so you have this waveform, you flow through my laser. Alright, it's almost like a straight line if you use together with a capacitor. Okay, whereas for the inverter, okay, which is the parts that you connect to this output DC, okay, you will basically try to change the frequency. Alright, because you are trying to convert back to this AC. Okay, right. So there's a few kind of technologies here. Alright, there's a few type of technologies that will be used in the inverters. As you can see, you will need diodes, okay, and transistor. Alright, it's basically a kind of diode as well. It's using a gate to fire or to switch on. Okay, and also a force commutation device. Alright, you need some bipolar junction transistors. So that's why you learn it in the part 1. Okay, and some other different type of transistors. Okay? So this is basically the components that you will see, okay, in these inverters. All right. So the PWM control inverters, okay, what is this? All right, what is this basically? Okay, this one have a flexibility of conversions, okay, from 0 to 500 hertz, and that definitely is a variable frequency. Okay, definitely you want to have the frequency that is changeable. Okay, we do not want to have a fixed frequency. Okay, and it has some form of to improve the harmonics, meaning that to reduce the noise. Okay, or that will be seen here. All right, that you can see later on. And there's a control input voltage. Okay, because this transistor that you know, okay, is always powered up by a VC or VCC that you know, alright? So there's a power up, okay, so you can control the voltage. Alright, so how this one will actually happens, okay? So what you will see from the AC to DC, okay, is just a square house. Okay, the very square, many houses as you can see from here. And what we want at the end of the day after the inversion is to get into a sine waveform, like the one that you see this dotted line. Okay, so in order to interpret this diagram. Okay, so the first thing that you will see, okay, you will have some triangular waveform, alright, some triangular waveform. And each of these triangular waveform, if you see that, let's say for this case, okay, if the triangle waveform is below this sine wave, okay, you will have a very high, maybe a voltage that's high. So anything that is above the sine wave, you will have a low, or almost a zero volts. Okay, all right. So you repeat the rest. So you will have a kind of a DC output, okay, from your AC to DC, the rectification. Okay, and then from there onwards, okay, you will have some sine wave. Right, that you go through the inversions. Okay, so you will see that another case. Okay, if you have let's say you change this amplitude of this waveform. Okay, or basically you are trying to change the frequency. You will see that the pulse size of this pulse will be a bit different. All right, so it's something like the pulse pulse width modulations. Okay, we try to modulate the pulse width, okay, to change to actually have the change in the frequency, right? Okay, so you can see that the difference between these both. Okay, the low switching frequency. Okay, so you can see that there's a gap in between each of these pulse. Whereas from this you can see that the gap is smaller. Okay, so this one have a very high switching frequency. And as you can see from the sine wave that's output from the inverter, okay, as we know that the inversion is to convert the DC to AC. Right, you can see that it's much more smoother as compared to the one that on the left hand side. Okay, so this is something that that we capture using a simulation, alright, just to give you a kind of idea. Okay, what is meant by the high and low switching frequency. Okay, so there's some other components that you can see here. All right, so because we are not in the there's no hands-on test or whatever, so just to give you a few. All right. So the constant DC link parameters, the capacitor is to regulate to the smooth voltage that you can see from the diagram below. Okay, we are trying to regulate the sine wave. Okay, the top part of sine wave to be more smoother to be a DC. Alright, so we use a kind of capacitor. Okay, but we know that these inductors, okay, is to smooth the currents. Alright, because we know that the currents is one of the parameters for the inductors. Okay, so there's many other components. Okay, we will not go into very detail, just to give you a kind of the rough ideas. What are the components that's available? All right. So what I mean by this type of active rectifications, all right, you can see that the output, all right, you can see there's a variable voltage. Okay, you can change the voltage here, all right, and at the same time, for the input, we know that it's always subject to the supply as well as the power factors and also some of the harmonics content, all right, some noise and so on. Right? Okay, what are the switching sequence? Okay, this one I think is not really is in the some of the notes in UK. Okay, but I just put this just for your information because this might actually explain much more clearly. Okay, so you will see that let's say you want to control a AC motor. Okay, so you through the DC. Okay, and there's an AC, DC, and to the AC again. Okay, so you can have there's some switches here. Okay, S1, S3, S2, S6. Okay, these are all the switches, and you know that switches can be transistors. Okay, transistor is basically a switch. Alright, if you send a certain currents to the base, it will act as a switch to turn on. Okay, without the base current, it will not turn on. Okay, so if you have a switching sequence like this, okay, a switching sequence. Okay, we have a switching sequence from V1 to V6. Okay, and this V1 meaning that the number 5 and number 6 and number 1, number 5, 6 and 1 will be switched on. If it will switch on, it will give you a kind of voltage, or I wouldn't say the voltage is a kind of let's say voltage with a kind of pulse width, the delay, as a V1. Okay, and if 612 is switched on, you will have V2, 123 is switched on is V3. So it's a switching sequence that we have. Okay, and you will see that later on. Okay, all right. This will be the result. Okay, this will be your phase voltage. This is line voltage. All right. So you can see that each of these pulse will represent a switching sequence. Okay, so this basically is trying to do a inversion that you can see that this one is almost like a sine wave. Okay, this one is almost like a sine wave. Okay, but at different phase, you can see that there's a phase shift, right? Because 3 phase, you know that it's 120 degrees apart, right? Okay, but when you look at all these technologies, okay, we will also sometimes link up to some of the very basic things. I believe some of you use a computer. There's in most of our computers, there's always thermal problems, okay, heat generation problems, because our processor is moving very fast. So a lot of heat is generated from the processor. So sometimes we have heat sink. Okay, or kind of thing that is attached on top of the processor. Okay, so to make to actually reduce the temperatures that's generated by this processor. You will see later on some of the example that I just attached. All right, and it's not in our notes. Okay, but just for your own information. Okay, and this one will also happens because it's also a power electronics. Okay, it will generate a very high temperature, can be few hundred degrees Celsius. Alright. And also some of the electric machines, alright, I will touch on more on the thermal side, but not on the EMC side, okay, the electromagnetic waveform. And there's also some distribution, protection, and regulations. Okay, the regulation parts I will not be covering because this one consists of a lot of these IEC kind of standards and so on. Alright, so I will try not to cover this, and it's not in the syllabus. Okay, and also some of the control that rely on the signal, so for the integrity and reliability. This one is I will show to you later on. Okay. Alright, so there's a few methods of doing a thermal protections. Okay, I will show you one of the methods. Alright, so you will see that some of the thermal power or thermal or heat dissipation. Okay, this power loss is basically our heat dissipation. Or sometimes we use a formula I squared R. Okay, to determine what is the heat dissipation. Okay, and all these device, the device itself, maybe for this case is the power electronics. Okay, and the casing. Okay, because some of the power electronics have some casing, okay, to protect the user from direct contact. Okay, and there's a heat sink to reduce the temperatures. Okay, it's basically a fin, okay, a series of fin, right? Okay, do you know why the dinosaurs has a fin on top of their body? It will reduce the heat because they generate very, very high temperature. Okay, so if they don't have the fin on top of this, so the heat cannot dissipate fast enough. So you will die of heat. Alright? So the same principle you will see from here is basically heat always transfer or move from high temperature to the low temperatures. So if you have a low temperature here, the heat will just travel. Just like a voltage. If the voltage here is high, the voltage here is low, like a ground. You always travel to the lowest resistance. Okay, that was towards the ground. So the same philosophy that you can see from here. Okay, so you will have temperatures change. Okay, this theta, here you don't use T, but we just use the theta to show that it's a parameter used for representing the temperatures. Okay, the theta J and minus theta A is a change in the temperature from the left hand side to the right hand side. Alright, it's a change in the temperature will be equal to the power loss. Okay, the power loss is in terms of watts. Okay, the power loss, as you can see from here, you can use the I squared R. And the RJA is the sum of all these resistance. The sum. Alright, if this one is 3 ohm, 4 ohm, 5 ohm, you just add 3 plus 4 plus 5. Okay, so you will have, so you know that how much change in the temperatures, okay, that heat sink will give. Alright, if the higher the change in temperature, the better, because it reduces the temperature. Alright. Okay, so you will see some of the device. Okay, some electronic device. They are cramped in basically two sides. Alright, and each of these sides is they actually use water, okay, to circulate to reduce the temperatures. Alright, so because here the heat is very high. Let's say we talk about is symmetric. So we just talk about the left hand side. Okay, you will see that the A part, it will generate a very high temperature. Because of the water that flow through here, okay, you will find that there's definitely this part will have a low temperature. So as the temperature will travel from the high to the low, so the heat will dissipate. Okay, and you can see that this fin, this portion, the fin, will help to reduce the temperatures further. Okay, so this is how this one will be used, okay, in some of the shapes. Okay. Alright, but we don't use this quite often because there's always a risk of leakages. Okay, so what happens if this leak and contact with the electronics components? I mean, we know that there's always a casing, as what you can see from here. There's always a casing, right? But however, we don't take the risk because if there's a short circuit, right? So the whole power electronics will actually affect the system's performance. Okay. All right. So you can see that this you do not have this slide, but I just show to you so that you have a feel that what is all this power electronics is about. Okay. So this is the fin that you can see a series of fin, okay, just like the dinosaur's fin. All right. And you have this what you call the heat sink. Okay, we don't say it's fin, we call it a heat sink. And there's a thermal pack. Okay, it's just a sort of insulation. Okay, and this is a power electronics. Okay, for this case, it can be a DC-DC converter. Okay, or it's an inverter also as well. So this guy here will give you 12 volts, the heat dissipation. All right. So to determine what is the temperatures change in the temperatures that this heat sink will give to this system, we basically use some formulas. It's the same as what you see, but in a different symbols. Okay, the delta T is just like delta theta. Okay, will be equal to the Q is the heat power loss, okay, times the total resistance R. Okay, for this case, the resistance is based on basically the material, the thermal conductivity of the material. Okay, this one is an inherent, okay, to the materials that you use. as well as it's depending on the kind of area surface. Alright? So you get 2 degrees. So meaning that from the base plate, let's say we start from 52 degrees, and what you will see or what you will experience further away from this electronics is 50 degrees. There's only 2 degrees of temperature loss. The higher the better, but this one can only offer 2 degree change. Okay, so you just imagine if the surface area is wider for the heat sink, you will definitely get a much more, the A here R will be lower. Okay, no, sorry, A is wider, so you will expect R to be smaller. So if R is smaller, that will cause the change in temperature to smaller. So it's not only for the A, you have to depend on the thermal conductivity of the material that you choose. Right? There's a standard table that you choose. Okay, so this one just to give you some of the terms that some of the industry really is using. Okay, what is meant by so-called enclosed natural. Alright, so there's no heat sink, but they just enclose it. Okay, ventilations. Alright, so this one is not so ventilated. This one is more. Okay, there's a hole there, to have the fresh air going in at one side, and the heat that can be dissipated out from the other side. Okay, this one is more driven, like forced convections. That basically you use a fan. Basically, this one we use it in the computer. Okay. Alright, so some of the good and bad design. Okay, this one again is not there, but just to give you a kind of a practical experience. Okay, you will see that this one is a very poor design. Okay, why? Because the power is actually situated near to the inlet, okay, of the ventilated design or the kind of sort of enclosure. Alright, so if this happens, you will see that this heat actually flow to those power electronics. Alright, so you generate more heat than reducing it. Whereas for this case, okay, the fresh air go in, but the power is at the end or near to the outlet, so it's quite okay. The heat just travel through the hole there. Alright, so it's depending what the design of your airflow. Alright, the airflow. Okay, some of this airflow we don't really depend on the natural airflow because the wind direction change and so on. So we don't rely on that. We have a fan to purposely generate the airflow. Alright, so you can see that this one is not shown, but there's a fan there. Alright, you can see that both. Okay, let's say for this case, okay, both of them there's a fan. Alright, so can you differentiate which one is open loop or closed loop system? Okay, based on the subject you have learned so far. The right side is a closed loop, yeah, and the left side will be definitely the open loop, right? Okay, how we know that one is closed loop and one is open loop? Yes, okay, but let's look at the left hand side first. Okay, the left hand side, you will see that this fan is basically you will adjust the voltage, okay, to the fan to increase the speed. I mean, as you know that the higher the voltage, the higher the speed the fan will turn. Let's say for example, okay, so you will actually generate more air to the power electronics. Okay, but there's no closed loop control. Alright, we do not know what is the temperature here. Okay, whereas for this case, alright, you still have the same input. Okay, and this input will be passed to the fan, then you will generate a certain speed. Okay, but the temperature can be monitored, okay, through the feedback. And not only that, there's a reference for you to make sure that the fan speed is what we want, okay, to the targets that we want, right? So I think that in the shipyard or in the ship, I think the thermal design is something very interesting. Okay, in some of the this engine room and so on, I think that it's really hot there. Okay, some of the subsystem and so on. So this is one of very good research area. want to look into the thermal design. Okay. So that's why you will see that why we use the thermal design kind of things to reduce the temperature is that some of the device will fail. Okay, it's not really because of the heat, but sometimes there's a short circuit, wire get basically exposed and so on. Okay, so these are some of the overcurrent effects. Okay, and if you use the fuse, the fuse is actually to disconnect the current transmission in the cable. Alright, but sometimes the fuse might not act fast enough to actually stop the high currents. Alright, so you let the high current pass, then it will fail, but it's too late. Alright, so this is something that you have to watch out. Okay, this one. Okay, these are the fuse. Those who do not know what is fuse, this is just a schematic diagrams. So in the fuse that you use, it will be something like quite a big size, not something small, 13 amps that you use in our power socket. It's a bit bigger in size. Okay, it's basically sometimes people call this as a circuit breaker. Right? It's just to break the circuit. Okay, once it breaks, you have to replace it. Okay, or else it won't work because no current will pass through. Okay, but some they can actually reconnect if the current get lower. All right, so it depends on which type of circuit breaker that you use. All right, so definitely there's always a case that we want to monitor it. Right, we want to monitor it. Okay, just in case that the fuse suddenly went off, cannot be used, no current for this one. So there's always a monitoring system in the control room, all right, to monitor all these states, the current states and so on. All right. So you will see that at this point, when there's a fault currents or any short circuit, when there's always a short circuit, meaning that there's some connections, is being exposed, or is being just connected directly to the ground. This is what we call short circuit. All right. You will see that the current suddenly go to zero. Okay. All right. It's currently very high and then go to zero. So it's something that you will see that kind of response that you will see. All right. In the short. Okay. When you see this one is you see when in the case of kind of fault, right? This one is with the circuit breaker. All right. Without circuit breaker, it will just go up. The current will be very high. All right. But with circuit breaker, all right, you will actually from this point you try to reduce the currents. Okay. All right. But when you say it's higher, if let's say the cable is being exposed, and that so-called exposed cable is on the ground. All right. So definitely, when someone touch it, you experience very high current. But it will be generated down to the earth. So sometimes you talk about the exposed time that you have short circuit. So the time frame is also quite important. All right. So these are some of the protection that we need to do. For over voltage. All right. We will try. Not to have a higher voltage. If there's anything, the voltage is not very not to what we actually expect. Correct. So it's something you need to watch out. Some overcurrents. That you use the fuse and so on to overcome that. And some of the thermal side that you have seen just now. Is some of the you can use the heat sink and so on to actually reduce the overheating. And this is something that cover this. All right, there's another areas for the fault kind of tolerance. What is mean by the fault tolerance? Okay, you will see that some of the power converters, okay, it's just not one single set. Okay, it comes with some redundancy. Okay, this redundancy is to help in case of one of the power electronics is not working. Okay, so it gives you some tolerance to fault. Okay, so sometimes we use the terminology called fault tolerance. Okay, it's more tolerance to the fault. Okay, and some of the motors, all right, is there's some separate windings. Okay, some separate windings that they have, all right, just in case that the main winding is not working. Okay, this is not very obvious to you. Okay, this is not very obvious to you, but you have to when you size the motor or you buy a motor, you have to ask if there's any case of a fault. Okay, can this motor still work? Do you have the separate windings and so on? Okay, but we know that this type of fault tolerance built into the system is very expensive. Okay, it's a very expensive. All right, so it's something that is it can be solved if you have budget on this. Okay. All right, this one is the same diagram that you will see. All right, so basically just to give you some of the terminology, symbols what this means. Okay, this is a cycle converter. Okay, you change the frequency. All right, this is cycle converter. Okay, this one you know. Okay, this one is the three-phase because all the three-phase is condensed in a single line. So we call this as the single line diagram. We don't show three lines. Okay, very complicated. We just show the single line. Okay, so generators. Okay, and you go to the kind of transformer. All right, a kind of transformer to step down because it's three-phase. We will need to have star, delta, okay, or Y, or so for the Y connections. All right, so for this is basically a rectifier. Okay, a rectifier because they don't draw the full circuit there. Okay, just kind of just to let you know that what it is. And you will see that why there's AC and why you need another power source here. Okay, you will know that some of the motor nowadays is an electric motor. Okay, there's power with some power electronics. Okay, so sometimes they need a DC supply. Okay, you cannot work AC. Okay, it's only the power source. Okay, it's AC. Okay. Okay, this one, all this winding and all this is something that just to illustrate some of the so-called extra winding, something that we have. Okay. All right, so you will see that all this there's always a circuit breaker. Okay, all this is hidden in the switchboard. Okay, you couldn't see that. Okay, on the line. All right, you will be in the switchboard room. Here is the main switchboard. Okay, it's all hidden at the cubicle. All right, and behind there a lot of bus bar. Okay, which is used to deliver very high currents. Okay, but the current is very high. All right, maybe a few thousand amps. Okay. All right, and you will see that, okay, below that, okay, there's always a further step down. Okay, you can see that it's a 6.6 kilovolts. Okay, it's step down to 440 volts. Okay. All right, so there's a few generators for redundancy, okay, for the fault tolerance kind of aspect. Okay, just in case that one generator fails. If I'm not wrong, the classification rule says that you must have at least two, right? Two or more. Okay, so you will see that there's always another emergency generators. Okay, all right. So you will see that some of these, let's say for this case, harmonic filters. All right, this one is to filter some of the noise because some of the equipment is very sensitive to the noise. Okay, some of this is very sensitive to noise. So these are something that we will use, and this one will be connected to the respective equipment. That is not true here. Okay. So you will see more complicated diagram than this. Okay, if you work in the shipyard, okay, or in the design office for electrical, okay, you will see most of this even more complicated. Okay, but for shipyard, I don't think you will be doing on all this electrical stuff. Okay, because it's being outsourced. You will not have the chance to do all the work. Okay. So you will just need to know that you don't get smoked by all the vendors. Okay. Alright, but it's a very good areas that if you can learn about this, okay, is because if you know about electrical systems, you will be somebody for sure. Okay, this is just to give you a summary of what we have learned today. Alright, just what we have learned for the first half. I will give you a break after this. Okay, so later on I will show you some of the catalogs. Okay, just to give you some ideas of about all this, what we have learned in all these power electronics. Okay, why you need to learn. Okay, so I went through some of the PWM inverters, all right, and some of the performance, okay, like the thermal side, and lastly the protection for forest. All right, so after the break, I will continue the second half. Okay, and next Monday, right, I will have the tutorial session. Okay, all right. So just go for 10 minutes break.